Okay, so this is part 3 for our Unit 6. Here we're going to be talking about polyprotic acids and how salts of acids or bases will change the pH of solution. So polyprotic acids are going to be acids that can contribute more than one proton to solution. They're going to dissociate one step at a time, so they're not going to lose everything all at once. It's like they hand their protons over first by one, and then the second, and then so on. Generally, the first ionization constant is going to happen pretty readily. The second one is going to be about 1,000 times less likely to happen. And it's going to continue in that manner so that the K values get a lot smaller for each step. So for example, for phosphoric acid, H3PO4 in water will ionize to give hydronium plus H2PO4 negative. This is that first expression. Now, technically, this over here can come down and behave as an acid by donating another proton to water to produce another hydronium and HPO4 negative. This HPO4 negative can, 2 minus, can be another amphoteric, there's two terms, I was trying to remember which one you're reading this. Amphoteric species, it can behave as either an acid or a base. By donating yet another proton to water to produce hydronium and phosphate. Each one of these K values becomes weaker and weaker as it continues on. Oops. I'm sorry. Thought I had another slide in here. Now, if we look, the only reaction here that really matters is going to be this first guy. And that's because it is so much more likely to dissociate than any of the others. You're only going to get a very small amount of hydronium from the second constant than you would in comparison to that first. So to find the pH here, we're just going to consider the hydronium that comes from this first ionization. And here we know 7.5 times 10 to the minus 3 is equal to, this is 1 molar, 0, 0, minus x plus x plus x. We're going to be able to discount this x because it's 1 is so much larger than this negative 3. So it's going to give us x times x over 1. 7.5 times 10 to the minus 3 is equal to x squared. Taking the square root of both sides, it's going to give us, not that, what on earth just happened? The wrong button. There we go. It's going to give us something like 8.6 times 10 to the minus 2. This is our hydrogen ion concentration. We don't want that though. We want the pH. pH is equal to negative log of our hydrogen ion concentration, or the negative log of that 8.6 times 10 to the minus 2. Can I fit it? There we go. Which is going to give us something like 1.06 or 1.07, depending on how much you rounded in your math. Now, generally, we can talk about it in terms of how much pH we have. We can also talk about the equilibrium expression or concentration of any one of these. I'm going to clean this up a little bit. And say that we now know we have 8.6 times 10 to the minus 3, nope, minus 2 molar here, and 8.6 times 10 to the minus 2 molar there. We know those concentrations. We can go stepwise until we have solved for everything until we eventually find our phosphate ion concentration. And that's what we're going to do. So we know here, for this second equilibrium, we have 8.6 times 10 to the minus 2, 8.6 times 10 to the minus 2, minus x, plus x, plus x. Because our equilibrium expression up here is 6.2 times 10 to the minus 8, our constant is so much smaller than these values, we can discount the x's. And so this is going to be equal to 8.6 times 10 to the minus 2 times x over 8.6 times 10 to the minus 2. Those cancel. And here we have HPO4 2 minus, concentration of 6.2 times 10 to the negative 8. Now at this point, we know down here that this concentration is 8.6 times 10 to the minus 2. This is 6.2 times 10 to the minus 8. Minus x, because some will dissociate, plus x, plus x. So here, our K value is 4.8 times 10 to the minus 13. Again, these values are so much bigger than our K value, we can discount these x's. And so we're going to be equal to 8.6 times 10 to the minus 2 times x over 6.2 times 10 to the minus 8. And we can solve for that x value here by saying 4.8 times 10 to the negative 13. We're going to multiply both sides by this 6.2 times 10 to the negative 8. You get something like 2.97 times 10 to the minus 20 is equal to 8.6 times 10 to the minus 2 times x. Divide both sides by that 8.6. And you should hopefully get something like, where'd it go? 3.6 times 10 to the minus 19. I actually, when I did this, I got 3.5, so I probably rounded somewhere on the last slide that I didn't here. But again, that's close enough because of the exponent being the same that it's essentially accurate. Now, this is technically way too long of a problem to give you on an exam, but it is really good to try this because you will see these on in your lab. Okay, now we're going to get into how the conjugates or components of different acids and bases will affect the pH of a solution when they're added as a part of a salt. Remember that all ionic compounds are called salts, and that when those are dissolved in water, they're going to split into their individual ions. Those ions, so say something like sodium cyanide, splits into sodium and cyanide. These two components can behave as acids or bases, and that is what we're going to get into here. So the salt of a strong acid and a strong base are always going to give a neutral solution. Look at KCl. KCl in solution splits to give potassium and chloride. K with hydroxide is a strong base, which means this is a very, very weak conjugate. HCl is a strong acid, which means that this is a weak conjugate base. That means that really K is not going to come in and react with water to give KOH, and H+. It's just not going to happen. The hydroxide is happier as a component of water than it is as a component of a strong base that would completely ionize. Same thing here. Chloride is a weak base. It is not going to come into water and steal an H to make HCl and leave a hydroxide. It's just not going to happen. It's much more content to be in this ionic form because it's a weak conjugate. And so therefore, you're not going to make hydrogen ion, you're not going to make hydroxide, you're going to have a nice neutral solution. If you have the anion of a salt that is a conjugate base of a weak acid, here, NaF, splits into sodium and fluoride. Na came from NaOH. It's a conjugate acid of a strong base, which means that this is very, very weak. It is not going to grab a hydroxide from water. It is going to leave it neutral. It's going to leave it as water. But HF is a weak acid, which means that this is a strong conjugate base. Strong conjugate bases are going to come in, grab a proton from water to make HF and hydroxide. It is more stable to be like this than it is to be with water. And so instead of having a neutral solution like on the last slide, we now have a basic solution. Same thing could happen if you had K with acetate. Potassium came from a strong base, so it's a weak conjugate acid. Acetic acid is a weak acid, so acetate is a strong conjugate base. It will take a hydrogen or a hydronium ion and leave behind the hydroxide. Remember that Kw is equal to Ka times Kb. So just keep that in mind as we're going forward here. An acidic solution is formed if you have the cation of a salt that is a conjugate acid of a weak base. NH4Cl splits into ammonium and Cl-. This came from ammonia. Ammonia is a weak base, which means that this is a strong acid. So it is going to quickly donate, let's do it this way, this proton over to give H3O+ and ammonia. So you get a nice acidic solution here. There's no charge. This is still a weak conjugate base, so nothing happens. So overall, you get a nice acidic solution. So just as kind of a flashcard slide, remember that if you have a weak conjugate, let's start over. A weak acid or a weak base, your conjugate is strong and will affect the pH of a solution if it's added as a salt. If you have a strong acid or base, the conjugate is very weak, and overall it's going to leave the solution neutral in the long run. Now, if your Ka is higher than your Kb, you're going to have a acidic solution. Your pH is going to be lower than 7. If your Kb is greater than your Ka, your pH is going to go up. It's going to be a basic solution because it is more favorable to form hydroxide and leave it in solution. If Ka is exactly equal to Kb, you end up getting a neutral solution, which just is relatively rare. So here, if we had Ka for a weak acid, something like acetic acid here, we can find our Kb. We know that Kw is equal to Ka times Kb. And so we have 1 times 10 to the minus 14 is equal to 1.8 times 10 to the minus 5 times Kb. Divide both sides by 1.8 times 10 to the minus 5. And our Kb here is, where did it go? There it is. 1 times 10 to the minus 14 divided by 1.8 to the negative 5. And you should get something like 5.56 times 10 to the minus 10. Hi, Titan. Right here. Lay down. Titan. Same way for the HCN. You can pause and try it on your own, but we know that Kw is equal to Ka times Kb. And so we can say 1 times 10 to the minus 14 is equal to 6.2 times 10 to the minus 10 times Kb. And so the Kb value for our Cn is going to be 1 to the minus 14 divided by 6.2 times 10 to the negative 10, or 1.61 times 10 to the minus 5 is equal to our Kb. Now, we have a solution of NaCN. We know in water that is going to split into sodium and cyanide. Cyanide came from the weak HCN acid, which means that this CN is a strong conjugate. Let me write it this way. If it is a strong conjugate, it is going to react with water to form the weak acid hydrocyanic acid and leave a hydroxide. Now, the Kb for this is HCN times hydroxide over Cn negative. And we know the K value because we can find our Ka. Kw is equal to Ka times Kb. So we divide both sides by our Ka, and we just did this. For Cn, it's 1.6 to the negative 5. Now, if we know 1.6 times 10 to the minus 5, I need more room. And we know that we're starting with 0.75, 0 and 0, minus x plus x plus x. This value is much larger than our k, so our equilibrium is essentially 0.75. This is going to be x and x. So that gives us our Kb is equal to x times x over 0.75. That gives us 1.2 times 10 to the minus 5 is equal to x squared, or x, if we take the square root of both sides, negative 5, you get 3.4 times 10 to the minus 3 is equal to x. That is our hydroxide concentration. So if we wanted to find pH, we need to go through a series of steps. I'm going to actually go up to the top of the slide to keep all of this nice and neat. pOH is equal to negative log of our hydroxide, which is the negative log of our 3.4 times 10 to the minus 3, which is 2.46 is our pOH. pH plus pOH is equal to 14. So pH is equal to 14 minus 2.46, or 11.5. So it actually does make a pretty big difference in the pH of a solution. And so we can consider exactly what is happening with the equilibrium. We can consider what our K values are, and we can really look at how much is true. So we know that with a strong electrolyte, This completely dissociates. We know that because this is a weak conjugate, it stays in solution. This is a strong conjugate, so it's going to force the reaction this way. So our dominant species here are going to be sodium and these guys. We could consider every single reaction that might happen, but because we know those two reactions that are going to be contributing the most, we can really just move forward with those. We know that technically this is going to have 1 times 10 to the minus 14, and really I discount almost any reaction of water if it's if the other K, the Kb here was to the negative 5. This is so much stronger than the negative 14. It's the one that's really going to be affecting our pH. So we set up our ice table and we're able to find our pH. Now, when we consider those type of problems, guys, set them up the exact same way we have been doing and just follow through that trend. It's really an interesting concept that you can adjust pH by adding in something that is not an acid or a base, but just simply the conjugate or a salt. We should get into some applications in class, but I'm not going to do that here. Now, in general, there are 2 factors that determine how acidic or how basic an acid can be, and those are bond polarity and bond strength. Now, the more polar a bond, the higher the polarity, the easier it is. Polar means partial negative, partial positive. The easier it is to break this bond off and to have the H plus just be donated to solution. Whereas something like go with HC, where it's more in the middle. This is a lot harder to have break off, and so you're not going to get as much donation. Another important factor is bond strength. The weaker your bond, the easier it is to rip off that proton and to donate it to solution. The stronger your bond, the less your pH, the less acidic your acid is going to be, the less your pH is going to be affected. So just to kind of keep in mind, HF, HCl, HBr, HI, all of these are technically acids, but the one that is going to influence it the most would be the ones with the weaker bonds. Here, the weak bond means that these guys can donate that proton faster. They're going to be considered strong acids. The acid here, the HF, that has a relatively strong bond, is not going to be split apart as fast, and it's going to be a weak acid overall. Now, one of the ways to really make a polar bond is by using an oxyacid. These are going to contain a polyatomic ion that contains an oxygen. Those have so much polarity. They influence this acid strength way more than bond strength alone does. This is the component that contributes the most to whether an acid is strong or weak, or is going to heal, is going to split and donate that H to solution faster. Okay? Now, the more oxygen atoms, the greater the polarity, the greater the ability to adhere to that strong polarity breaking apart rule. Let me just show you what I mean. HNO3, HNO2. This has got more oxygens. It's much more polar. This is going to be able to donate that H plus very, very quickly. This is the strong acid. Meanwhile, this has fewer oxygens. It's not as polar. It will donate an H plus, but not as readily. So this is a weak acid, which is why in our strong acids, HNO3, interesting. HNO3, H2SO4, and perchloric acid, these are the ones in their series that have the most oxygens. Nitrous, sulfurous, chloric, and chlorous acid are not nearly as strong as these guys. And this just kind of goes in and shows you again, the more polarity, the stronger the acid. Now you can have acidic oxides where you have something like SO2, and when you dissolve that in water, when you dissolve this in water, you're going to technically be able to form a relatively weak HO bond, and you're going to release a proton. You can kind of see that this would reform to make H2SO3. Basic anhydrides are very similar. You're going to have CaO and water. Because you have a low electronegativity, the OX bond is going to be ionic, and it's going to be broken by the more polar water, and it's going to produce a basic solution. So here, this plus this gives calcium hydroxide. And while I don't expect you guys to know that, I do expect you to know what a basic anhydride really means definition-wise. Now, everything from to this point was really dealing with the Bronston-Lowry definition of acids and bases. We're now going to get into Lewis acids and bases for a minute. And a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Here we have a Lewis acid because aluminum can accept electron pairs. This is a Lewis base because it has lone pairs to donate. And so you can end up getting a coordinate bond here between the water and the aluminum. And you can actually form overall a complex that is just as stable as some other molecules might be. So here's another type of flashcard slide where you have the 3 definitions of acids and bases. And when you're looking at these, again, make sure you're always considering what major species are present, how strong is each reaction, meaning look at your K value, what equilibrium or what reaction is going to dominate overall, and then just follow the steps to get to the answer. Some of them feel really long, but because there's more than one way to answer most of these, you may have just picked the long way. It doesn't necessarily mean you're on the wrong track. It just means it may take you an extra 25 seconds or so. Now, way back in unit, 3 or 4, we talked about Lechantiers' principle. And we said that if you added in something, it was going to shift the equilibrium to relieve that stress. This is the same concept, it's just that now we're going to be calling it a common ion effect. If you add in an ion that contributes to one side of the reaction, it is going to shift the equilibrium from that stress to the other side of the reaction. So for example, if you added in NaCN, NaCN is going to ionize to give Na and Cn minus. Cn minus, if we add some of this in, is going to cause the equilibrium to shift to the left. So when you add this in, you're going to decrease the concentration of H3O plus, and you're going to increase the concentration of the guys on this side of the reaction on the left. And so you can actually kind of have a discussion over how the pH or how the shift of this reaction is going to occur. And so if adding in sodium cyanide is going to make this solution less acidic because of that shift. And you guys are going to see this in lab as well. All right, I'm going to stop here for part 3. And we'll do buffers and titrations in the 4th video.